We're just going to keep waiting until people join, and then we'll start in maybe a couple of minutes. Okay, looks like most people are in. So I'll start. So thanks very much everybody for joining. Um, we've got modeling sustainable drainage systems webinar today, organised by the UDG New Members Group and delivered by the guys at McCloy Consulting. So I'll just do a quick introduction, go through some housekeeping, and then we'll get started. And then towards the end we'll do Q&A. So yeah, please use the Q&A function as we go. So yeah, housekeeping. This webinar will be recorded and will be put up on the CIWEM YouTube site where you can see all past events. If there's any technical issues, please raise your hand and put any queries in the chat rather than the Q&A, and one of our team will come and try and help you. As I said, yes, we'll take questions at the end and use that Q&A facility for that. This is 1 hour CPD, but I'm not handing out any certificates. So, quick wee bit about CIWEM. So, Royal Chartered Professional Body and an independent charity. So, the mission is to improve water environment management for the public. We've got over 11,000 members. And the vision is to produce a world in which professionalism and excellence build connections to inspire widespread, impactful water and environmental solutions. And then just a wee bit about us at the new members group. So we are part of the UDG. We're the UDG new members group, and really we've been set up to support the professional growth and development of pre-chartered members within the UDG. So we're looking to provide initiatives that will support each other's progression in the industry. So we've got 4 key areas that we look at, and we're split across these areas. So we've got the events team focused on providing events like today, as well as supporting the UDG at all the UDG events themselves, including our annual conference, and we'll be there this year. I think we're going to have a session, which is very exciting, and we'll be there to kind of support people that are newer to the industry there. And we have the guidance team, which is we support the main committee in developing the UDG's latest guidance, and then the membership team looking at CIWEM chartership, and then the comms team, and we're focused on just creating a conversation with our new members, and keeping you up to date on what's happening within UDG. So you can get us via the link there. So I will move on, and I'll let I'll let Michael, I'll let you share as I introduce you guys. So today we've got looking beyond peak storage and flow, SuDS and hydraulic models. So presented by Anthony McCloy and Michael Rea. So Anthony is the managing director of McCloy Consulting, and a specialist in water-focused multidisciplinary with nature-based solutions, flood risk, landscape design, and so on. I think Anthony's given more than dozens of similar training and presentations like this before. He's a well-known face. And then Michael's a senior engineer at McCloy Consulting, joining from Queen's University, Belfast in 2017. He has extensive experience in flood risk and drainage, specialising in hydrology and flood estimation. So thanks, guys. If you want to.
Yeah, thanks, Alan.
Cheers.
No, thanks for the opportunity today. It's a really interesting topic, and I think it's one that is very much still, for me, in its infancy. So today, it's really more about scene setting and looking at some of the things that we could be considering that we don't normally consider. So I'm just going to do a couple of slides, and then I'm going to hand over to Michael just to sort of get that introduction piece. I suppose my first introduction to SuDS was back in 2003, and I was working for a large multinational at the time and working with a number of water companies, and one of them came to me and said, we're looking at doing some method of intervention to solve these CSO spills and flooding downstream. Is there any way we could do something that wasn't just upsizing the pipe, putting a pump station in, or putting an underground tank in? And that led me to discover the first SuDS manual that was published back in 2000. And really, from that point onwards, looking at SuDS in a different way. So that very much led me down a different career path. And I now have a company, and just very briefly about us, we're a company, we're a well-established company at this point in time. We're sort of approaching 40 people on staff, and we are very much multidisciplinary. I think one of the appreciations I've gained over the years at SuDS is very much multidisciplinary. It's not just about one person doing one job, it's about how you get that range of people. So we have in-house landscape architects, ecologists, hydraulic modelers. We have a large number of hydraulic modelers within the company, and civil engineers, and the list goes on. So it's getting all of those people to work in one team and work very much symbiotically. So there you can see, you can have a look at our website afterwards. That's sort of the key people within the organization. And a lot of those are covering key business stream, whether it's environmental, civil, flood modeling, geo-environmental, landscape. So we have a number of good, strong individuals there leading up certain sections of the business. So yeah, it's exciting times. We're seeing a lot more opportunities in nature-based solutions. I've just come out of a meeting where that seems to be the main trajectory forward in terms of solving a lot of the CSO problems, a lot of the flood issues, is looking at it through SuDS and nature-based solutions. Next slide there, Michael. So yeah, you can have a look at our website. I'm not going to dwell on us as a company any longer than that. We get involved in a lot of interesting work. A lot of nice niche projects, a lot of large scale projects, and yeah, it's been an enjoyable experience to date. Next slide, Michael. Just to basically cover on SuDS, it's always good to start with getting a common benchmark across the talk, and just giving that definition. And really, for me, from day dot, SuDS has not been about drainage. It's been about placemaking. It's been about urban resilience. It's been about a range of different things, all parceled up as an approach. So whenever I see SuDS and somebody talks about SuDS and they say, well, there's our SuDS tank, that's our SuDS, very much I'm always slightly dismissive in terms of, well, that's not SuDS. That's not the approach that we're trying to apply here. we need to, if we're going to do that, we need to, how do we bond it into something else? So it needs to look and see how it falls in under those sort of key definers in terms of, yes, absolutely, we impact on quantity and quality. We try and improve the quality of runoff. Even if it's going into the combined sewer, we try and reduce the quantity, both in terms of overall volume and rate. But we also look for opportunity to maximize benefit for both people and nature. So we can do that as long as we take the right approach. We look for the right opportunities. We work with others. So it very much, Michael, next slide. So that's it in a more graphical context. And really, I've found over the years, it requires certainly a different mindset. You're looking for different opportunities. But I am seeing the new generation coming through are very much up for the challenge. I have found in the past, there have been a few resistors in the industry, generally people who have been doing it one way for their whole career and suddenly come along and say, well, actually, that way doesn't work. It doesn't achieve all of these other things. We need to think about it differently. You do find that you meet resistance. There's a bit of inertia, but I do find that the younger graduates we have coming into the company and others I've met throughout the industry through UDG Group and elsewhere, they're very much this is our future. We want to make it better and we want to maximize, and they're excited about that opportunity. So I hope that the audience here today are as well. Michael, next slide. So just to recap, we're probably all well au fait of what way we conventionally capture rainwater in terms of our urban systems. So it comes onto hard surfaces. We have gutter lines, we have points where we'll direct rainwater, and then it will go into a small opening, so a channel or a gully pot down into the pipe. We find that gully pot, a lot of the time where we have really intense rainfall or steep slopes, water doesn't actually enter that gully pot. It skips over. There's a hydraulic jump, or the gully pot may not have been maintained for the last 5 years and it's completely full of silt and acting as its own bioretention, but not letting any water through it. So we appreciate that the systems we have, the legacy systems do a job, but don't necessarily do it to the right requirement that we're now requiring in terms of the intense rainfall cloudbursts, in terms of removing pollution, in terms of keeping water part of the landscape that will make benefit for people and nature. So we're trying to both utilize what we have. We're not going to bin it. We're not going to chuck it out, but it's how do we hold on to that, and how do we make sure that new systems coming forward and new development, that we take a different approach. So next slide, Michael. So this is a scheme, and Michael will probably chat about it later on, so I'll not spend too much detail on it, where all of the landscape in this residential community was very much conventionally drained. The scheme was not focused on flooding, it was focused on water quality. The water course is quite small that receives runoff from that big, massive residential area. Is heavily polluted. It doesn't achieve its water quality status. And they were looking at ways of rejuvenating that water course by improving the water quality. So you can see that it's more than just one driver here. There can be multiple drivers, and depending very much where you get the funding, maybe where your focus is, but you shouldn't lose focus on all of the other things. So it's very much a multifunctional thought process that you're trying to do lots of things. You're trying to do them everywhere all at the same time. So it's very much looking right across the catchment, looking at every opportunity you can do to do things at source, looking at things that will multiply up in terms of, well, do we actually need to do better placemaking in this area? Is there need for traffic calming measures? Is there need for rationalization of parking spaces? Are we getting active travel involved? So it's looking at how we combine all of those things to be multifunctional, but then also, as we're doing that, get betterment in terms of how we manage rainwater and do that all part as one parcel. So we have to be really sympathetic in terms of in terms of existing landscapes and the host landscape, particularly in SuDS retrofit. that these are not heavily engineered schemes. These are things that add value to the community, and the community very much, if you do it properly, they absolutely love it. They think it's fantastic and they want more of it. So as a design community and hydraulic modelers and engineers, we need to ensure that we don't impact that process. We keep delivering things that add betterment, that add value. Next slide, Michael. So very much that idea of multifunctionality, the multidisciplinary approach. So we're thinking about a whole range of different things, and we all have a part to play. And I think hydraulic modelers, for me, the scope that we could be contributing to can only evolve over time and expand. And we need to start thinking about a whole range of different things and how we work with others. So a hydraulic modeler working with ecologists isn't something that would normally spring to mind, because generally speaking, as hydraulic modelers, we're worried about flow rates and volumes and peak levels. But in reality, in terms of designing a landscape for ecology, you're saying, well, how often is that area going to be wet? How often, how much water and what depth, and how frequent will that water be there? Not just in the extreme storm event, but on a day-to-day basis. So after small and very much moderate volumes of water, what is that going to look like? What's that going to feel like? How will nature react to that? And what sort of planting might we use? What sort of habitats might we create? What sort of wildlife or nature might we be able to introduce into that area? And the same then applies for people as well. It's exactly the same types of thought processes, of approaches. So it's very much, yes, we absolutely still think about exceedance flow rate. We still think about mitigating for flood, but we think about all of the other aspects as well in terms of where we can add value as hydraulic modelers and as engineers, looking at that water cycle and that water process. Next slide, Michael. So this is a scheme, again, we've had involvement in. It's quite a famous scheme at this stage in terms of UK, Sheffield Grey to Green. It was a council-led design. Myself and Michael were both involved in it in terms of the hydraulic modelling and sizing of all the flow controls and the flow conveyance, and really interesting scheme that for anybody who's ever up in the Sheffield direction, how much nature-based solutions and SuDS are now embedded within the highly intensive density of the internal city itself. So we can be using that hydraulic analysis to inform a lot of things in terms of how much water those plants get, how much water are we taking out of the combined sewer. On this one, all of the water went to the combined sewer, but you had the River Don that runs through the middle of Sheffield, literally about 100 yards away from where the outlet was in terms of going into the combined sewer. So that was a diversion out of the combined sewer, full separation, and a redirection into the River Don. So the amount of saving there in terms of carbon costs for treatment, pumping costs, and conveyance costs, and freeing up capacity for future development for file input into that combined sewer is significant. So we can use the hydraulic calculations and the hydraulic modelling to inform quantity and quality, but as I said earlier, looking at it from a immediate biodiversity as well. So there's a whole range of things. SuDS is not just about water, it's about air cooling. And the last couple of weeks, very much in terms of the temperatures we've been getting across UK and Ireland and elsewhere, across Europe, would lead us to think, we need to get more of this type of infrastructure within our cities and towns to make them more livable. So really it's about that air quality, urban cooling, climate resilience, and health and well-being. Next slide, Michael. So yeah, I'll just round up before I hand over to Michael here, and he'll talk you through a few case studies. It's that taking what we sometimes approach it as very much a narrow viewpoint of things we're trying to deliver in terms of flow reductions, thinking about a wider context in terms of interception losses and how we can lose water across an urban landscape, and slow that water right down from the point at it's collected and hits the ground, because that improves urban cooling. It improves the water quality in terms of the time of retention as water moves through the system, whilst also be given that provision and making opportunity for nature. So it's that realization that we have an integral part to play, but there's a much bigger picture there as well. Thanks. Michael, you're maybe up next.
Yep. Thank you, Anthony. So this section I'm going to go through is about how SuDS can be considered within hydraulic models. The key point I guess I kind of want to make is that modeling SuDS should not just be about asking, does it store enough water? Does it restrict flow to targeted discharge rate? Those are important questions, of course, but they're not the entire picture, as Anthony's pointed out. A useful model should also help us understand how the SuDS work, where the water is coming from, if that water can reach the feature, how it be stored and conveyed, what assumptions would matter, and where does the water go if the system exceeds. So I'm going to look at a couple representation SuDS, different modeling scales, assumptions, and a few practical examples using case studies that we use, sort of causeway flow for a 1D drainage model, and Inforx ICM as a 1D, 2D catchment scale model. So modeling can help turn a SuDS concept into evidence. The clips on screen are ICM model outputs from an urban park as Queenswood and Haringey in London. So in the existing scenario on the left-hand side of the screen, runoff followed a natural valley through the park. It wasn't really that defined like rivers, but it was defined flow paths. And during intense rainfall, that created a fairly flashy response with water collecting and moving quickly towards the downstream drainage system. And there's an old sort of former flood defense there that you can see on the screen, bit of a wall to try and hold that water back. But it quickly got overwhelmed and flooded sort of downstream. In the proposed scenario we tested a series of basins and leaky dams that are placed along that flow route. And the purpose of that was not just to provide a single sort of storage volume. It was to intercept that flow, slow it down, and temporarily slow it and release it at a more manageable rate downstream. That means that the downstream drainage system is less likely to be overwhelmed and flood risk is substantially reduced. And this is where modeling is really useful. It helps put confidence behind the design. It shows that change in flood mechanism and provides evidence for stakeholders. And so that's sort of like a statutory body, the public themselves, or in this case, it was funding an outline business case. So probably instead of simply saying we have added SuDS, the model helps demonstrate what the SuDS actually does. So if we break modeling into 4 parts of what we're actually trying to represent, first is inflow. What water is the system receiving, whether it's direct rainfall or overland exceedance? Is it feasibly direct, or are there complex mechanisms happening prior to the flow reaching the feature? Second is conveyance and storage. How is that water being moved and stored? Third is processes. So what happens to the water while it's in the system itself? That might include infiltration losses or other stuff that can just slow it down. And fourth is outflow. How does water leave? Is it controlled via flow control, discharging to a pipe network or overground, or is it making a surcharge outfall in, say, a watercourse? And that framework works while we're looking at a 1D site sort of scale drainage model or a 1D, 2D catchment model. The level of detail changes, but the basic questions stay the same there. So yeah, one of the key things is scale. So at site scale, particularly in a 1D drainage model, we often treat SuDS as engineered assets. We have a pretty good understanding of inflow. We're asking whether there's enough storage, whether controls for size correctly, and whether water levels and discharge rates meet the required standard. The strength of 1D model is that it's relatively quickly to build and run, and it's well suited to test sort of storage volumes, flow controls, critical storm durations, and compliance requirements. But the main limitation is that overland routing and exceedance behavior can't be simplified unless it's linked to a form of surface representation. But even then, it should still be quite simplified or quite simple representation. Moving over, so at a larger scale, say a catchment 1D, 2D model, the question's a bit broader. We're asking how SuDS intercepts and changes the way water moves through the area. And that might mean testing whether water can physically reach the feature, whether an overland flow route is diverted or slowed, and what happens when the system is exceeded. The strength of 1D, 2D model is that it can represent surface flow routes, low points, exceedance pathways, and wider flood mechanisms. But the limitation of a 1D, 2D model is that it's much more data intensive, run times are significantly longer, and smaller SuDS features may need to be simplified because they're below the resolution or accuracy of the ground model. So at one scale, the SuDS feature is mainly a storage and control asset. At another scale, as part of the wider flood mechanism. And as an example of a 1D drainage model implementing SuDS, the first case study that Anthony mentioned before was McCloy as part of the Dublin Rainscapes project, and modeled this using causeway flow. This was the first and largest of 5 pilot sites commissioned by Dublin City Council to reach construction, with the aim of improving water quality as well as helping manage quantity of runoff within the River Santry catchment. It was a distributed SuDS scheme across 3 residential estates designed to intercept highway and hard-standing runoff before being discharged to local storm sewer network and ultimately towards the watercourse. And the key point here is that SuDS were not designed as isolated features. They were formed as part of a management train, with runoff passing through a sequence of rain gardens, permeable paving, swales and basins before its eventual outlet. In total, the scheme intercepted about 2.5 hectares. The design itself was landscape-led, so the hydraulic modeling was not the whole design process, but it helped to benchmark performance, inform the flow control sizing, and support the case for wider SuDS rollout. So this is a good example of a 1D model being used to test how a distributed management train performs, rather than just simply checking whether a single attenuation tank has enough storage. This slide shows how the physical SuDS features were translated into the model. I won't read for each row, but for example, rain gardens were represented using depth area storage. That included the surface storage, but also the storage within the soil strata and the porosity there. Interception losses were also represented to capture the first sort of 20 millimeters of rainfall entering the feature at the start of the run. That's about 10% of the topsoil depth. And the reason that matters is that interception losses represent the volume of runoff entering the SuDS system that then doesn't leave through the flow control. So for another scheme we did quite a few years ago at Bridget George Square, or Australia Road it was first called, interception losses as the planting became more and more established, significantly reduced the amount of rainfall that was required before an outflow was even measured in the downstream manhole. So this model itself was still a simplification, but it's trying to reflect the actual behavior of the SuDS, where water is stored, where it'll be lost, how those features connect and interact with each other, and how the water eventually discharges. The model at McCloy helped to show that performance was not just about total storage volume. Feature type, connectivity, available volume, loss assumptions, and critical duration all influence the results. One important finding was that linked features performed much more strongly than isolated units, which reinforced the idea that SuDS often work best as a management train. Another key point was that the interception losses mattered. Testing with and without losses changed the predicted volume reaching the sewer, particularly in the lower return period events. So to demonstrate a SuDS retrofit in a urban setting with a 1D, 2D imports ICM model, we've got a second case study located in Larkspur Close in Haringey. So this was a retrofit SuDS scheme supporting an outline business case, and the aim of it was to use SuDS as a targeted relief measure in an urban environment. The scheme intercepted a relatively small direct catchment, around 0.2 hectares, but it was also intercepting two main overland flow routes of urban exceedance and surface runoff of gradient in the catchment down the Jellycombe Frat roads. The site itself also had the added complication that surcharged in the cell watercourse to the south of the site. The bank walls in the cell were higher than the main body of the site, so discharge was limited from the site at high stage in the river. And a 1D check could have confirmed the storage and control discharge, but the real test was whether the scheme reduced flood risk once the wider 1D, 2D mechanism was represented. And it's important to say that this wasn't intended to remove all the flooding at the site for all events. The flooding in the picture at the bottom of the screen was from a two-year equivalent event with blockages and non-return valve failures. The brief of the site was to target these more frequent nuisance flooding events with that residual risk acknowledged for the larger events that could occur. So just briefly, the solution for the site was to divert the existing flow routes on the Jellicoe and Frat roads using raised tables on the road and gullies to capture that runoff. And those gullies outlet into a swale and eventually into a basin, providing temporary storage with direct outfall to the cell watercourse down gradient. And within the site itself, permeable pavement and rain gardens provided temporary storage within the site for the direct catchment at times of surcharge. So just giving a place for the water to sit and store before it can discharge. In the 1D, 2D model, elements such as rain gardens and permeable pavement were represented using 1D storage connected to the 2D surface. Benefit this was being able to model the substrata volume storage in a similar way by altering the volume basin porosity. And the basin conveyance routes were represented by edits to the 2D ground model. So the model can test how water moved through the scheme. Flow controls were also represented using orifices and overflow weirs. And the outfalls were also important. The full catchment was simulated to represent how water was being influenced by downstream conditions up in the cell. So the wider model was needed to test not just the feature capacity, but the full flood mechanism. And so the 1D, 2D model helped show both the benefit and the limitations of the scheme. The scheme changed the flood mechanism by intercepting upstream overland flows and providing temporary storage on the site at times of surcharge. The benefits were strongest in the frequent, more nuisance events. The model showed an average property depth reduction of about 150 millimeters in the 20-year event, reducing to only about 40 in the 75-year event. And that pattern's important. It shows the scheme was useful, but also became overwhelmed in larger events. So the modeling supported a proportionate outline business case with model benefits to 37 properties, whilst also making residual risk clear. And to deal with the residual risk is recommended sort of implementation of catchment-wide SuDS to reduce peak flows within the cell and wider storm systems. And so just design storm is not the whole story. So a lot of drainage design is quite understandably focuses on the design event. We need to know what event sizes, the storage, what the peak water level is, whether there's enough freeboard, and whether the system meets the required standard. But with SuDS, the design event doesn't need to be the whole story. These systems also need to work day to day. They'll need to deal with regular rainfall, first flush runoff, and everyday wetting and drying that actually shapes how the space performs. And that's where landscape design becomes really important. So for this example, the SuDS were integrated into the public realm. In smaller but more regular events, water may only wet the bottom lower part of this feature. But additional capacity is still built into the landscape for larger design events. So the space can function day to day without feeling like flood storage, while still providing that extra hydraulic capacity when it's needed. And just to finish up, just SuDS modeling depends on assumptions. That can be from inflow hydrology, losses to infiltration, how vegetated it is, the stage of that vegetation, if it's established or newly replanted, roughness and outfall conditions, and any other external factors. The performance of the SuDS system will change season to season, as we've found in sort of monitoring exercises on Bridget Joyce Square previously. The answer is not to pretend those uncertainties don't exist. The answer is to make the important assumptions visible and test them where they matter, and communicate to the client or the stakeholders how things will change through time. That might mean testing with and without infiltration, testing with more initial losses, increase or decrease roughness, or considering that reduced outlet capacity. A useful model is not one with no assumptions. It's one where those assumptions are clear, proportionate, and explained. And of course, caveated with the all too familiar, all models are wrong, but some are useful. And that concludes our part of the presentation, my part.
Perfect. Thank you very much, Michael and Anthony. That was really interesting. I think we've got quite a few questions to start on. If I can share my screen again, and then just start looking at these questions. So if anybody's got any more questions, please put them in the Q&A part of the Zoom, and we'll get to them when we can. So I think the first one, I think Anthony, you've already been on these ones, but
Yeah.
if we want to speak about some unanswered ones, so Prashant, SuDS integrated drainage models are notoriously hard to calibrate given limited outfall monitoring when working to WAPOG verification standards. How do you evidence model performance for the SuDS components specifically? Are you placing monitoring within individual features or relying on upstream, downstream sewer flow records?
I think it's probably a mix of everything, to be honest.
Yep.
I would agree that monitoring around SuDS, we have found in the past to be difficult. You really need to know what you're doing.
Yeah.
There is sometimes a bit of reliance on worldwide research. We have this is not a standing start. A lot of this stuff has been researched, particularly around the quantitative volumetrics around what happens in certain soil conditions and certain features and certain flow controls. So there is a lot that I don't necessarily think we have to try and absolutely calibrate and verify, because we know we have a good indicator of what the performance will be. And if we do a like for like scenario, we don't necessarily build the sewer and then go out and calibrate it afterwards, because it's a similar idea.
Yeah.
I think the code of practice is mentioned here, WAPOG code of practice, which is still a really good document. I don't necessarily think it's fully compatible with where the industry now is in terms of looking at SuDS and how SuDS models might be calibrated. I think it's more predominant around the conventional drainage system, where the whole WAPOG came out of managing sewage, managing rainwater within a pipe. And if we're no longer doing that, then there probably is different ways. So it's not necessarily always about a Doppler at the bottom of the pipe. It might well be a whole range of different things in terms of setting up videography and just the camera, looking at rainfall, looking at different rainfall events. I think that we need to possibly go back to a bit of the drawing board around how we calibrate these SuDS models, and also think about it in terms of the no regrets, in terms of if we're doing this and we're doing it for all our reasons, if we can bond in additional water management measures we know will provide benefit, then there's no regrets there. So we don't necessarily have to calibrate everything that we design. So there's a range of different things there. It's no straight answer, unfortunately.
Yeah. I suppose like that situation of having a kind of SuDS integrated model, like SuDS are becoming more and more commonplace in drainage systems. So we're I suppose at the moment most of the times we're dealing with SuDS as we're designing them, but more and more it's going to be how are we understanding that performance.
There's going to be a lot more. Yeah, go ahead. Sorry.
Yeah, no, just maybe even like 10, 15 years down the line, we're kind of looking, is this still operating? Well, is it operating as designed? And does it need to be done to kind of to put it back to the original standard and that sort of work?
Yeah, I mean, a lot of the good examples of SuDS, you look 10, 15 years down the line, and you're sort of not saying, is it still operating as it was designed, or is it now operating better than it was designed?
Yeah.
So we have a few examples where we've had significant cloud bursts, and we're looking at the scheme, and the scheme's not filling. It's not utilizing storage, and you're sort of questioning why, and you're saying, well, in reality, the modeling and the calculations that were done at the outset were probably conservative. They didn't really take into account all the losses that were going to happen over time. So I think that whole sort of science piece and thinking about it from a realistic point of view rather than a conservative point of view, we probably need to take be a bit more cavalier or more demonstrable. And as Mike was talking about that, those sensitivities in terms of saying in year one it might operate like this, but in year 5 it could well be operating in this way, and thinking about that from the outset. So it's not static. I think that's the key, and not treating it like that.
Yeah, no, absolutely. I hope that answers the question. I think we did. Joe Bradley from Stormwater Shepherds. How can soil selection in rain gardens and swales affect the performance of the feature?
I'll maybe take that one as well. Yeah, I know Joe for quite a while. Didn't expect her to be on the call here today, but there you go. There's a range of things in terms of what is it you're looking to plant in there.
Yeah.
What's the underlying geology? The pH of the soil will affect the cation exchange in terms of its ability to absorb pollutants. So there's a range of things in there, and I think we'll probably need another full day to get into that in full detail. I think the key thing for me is not to disregard it as don't need to worry about it, is to think about it actually as something that is quite important in terms of soil selection. In these sorts of features, for me, it links into another question around a description around a rain garden. I think as an industry, we have started calling everything rain gardens. Where the terminology first came out of was the States, and it was very much a garden feature that was a depression in the garden that took runoff there was no real pollution. There was maybe a small degree of pollution, but not significant pollution. But what we're now doing is applying that in a highly urbanized, highly polluted context in terms of highways and roads, which Joe will be interested in. And that's, for me, is where you get an engineered topsoil. And I generally like to distinguish between a rain garden, which is a simple planted depression, and a bioretention, which is an engineered topsoil that is required to be designed in the way it's designed. So if I am going to call it, I generally call it a bioretention rain garden rather than just a rain garden. So just to explain around that bit of terminology.
Yeah, I think like my experience is like quite often that things like that kind of the soil, the topsoil, like the porosity and all that. like from my background, I'm going, how much water can we fit in that soil pore space? But actually, the considerations are a lot more complex in that you're actually thinking how, especially if we're involved in some sort of planting, it's kind of like how do we keep these plants alive? Not only
That's
during the flood condition, but during the dry condition as well. And it can get, from my point of view, quite complicated quite
you've
quickly.
hit the nail on the head there. I think a lot of the specs we've seen to date are very much hydraulically driven in terms of getting loads of water either through the system or holding it within the system without actually considering how are these plants going to be self-sustaining for the next 15 years without applying fertilizers and mulches, which we don't want to do.
Yeah, absolutely. Okay. Question from Annabelle. We'll just keep going with these. Does the basin type solution have any issues with becoming standing water, particularly near residential areas? It's probably quite a common issue with the SuDS features. I don't know if you or Michael want to.
Yeah, I'm happy to chime in. Michael, you can chime in whenever you want. I don't want to dominate the floor either. Yeah, it's probably working out where the perceived concern is coming from, what angle it's coming from. I mean, a pond is standing water, but we have ponds and canals and everything all over our urban environments. Generally, it's usually born out of two or three common concerns. One will be the concern around the going septic and stagnant. This is low nutrient water. If there's loads of nutrients in it, it's probably an indicator there's something else getting in there that isn't stormwater. So generally, we find that every time you get that rainfall, you get that flush of additional water, getting something that it won't go septic and stagnant. That's not what we find in SuDS systems. Second one's generally health and safety. Having standing water and concerns around health and safety. And again, that comes back to the design. That you're designing for safety, you're designing with consideration of who are the users of the site, how are they going to access and egress. Fencing is not the solution. Fencing, for me, generally increases the risk. And then the third one is probably, vectors and mosquitoes and other types of, are you creating habitat? But again, it goes back to design and proper habitat ecosystem creation. So if you get an ecosystem created, you generally don't get the same issue with the vectors and mosquitoes, etc., that you would get from a puddle or a bit of standing water where there's no vegetation around it.
Yeah, no, absolutely. Yeah, I mean, I think like again, reflecting on like my experience with it, kind of like, again, from a flooding point of view, I want to fill a basin with as much water as I possibly can, keep it out, keep it out of where it's not supposed to be. But am I right in saying that generally the push is more for these features to kind of, we want to be kind of not having too much depth of water in them at all, even for obviously a reasonable amount of time, so we're not keeping there for a long time, but as in we want to be closer to sort of 100 mil, 200 mil, rather than having large basins that have got real big depths of flow in them for any significant amount of time.
I think we've had a history of developing heavily engineered structures that look more like big swimming pools and large craters. I think there is, I think for me, the move should be, and I can see it tentatively going in that direction, it's moving away from having a single feature in a single location and trying to get as much water as quickly as possible to that location and hold it centrally within that location, which is generally where you can get in the steep sides and deep, because everybody's trying to maximize everything, to more of an integrated design source control, where you're trying to limit flows getting to that point. And I think that, it's similar to retrofit, similar to new design, and in particular new design. If you're just designing a pipe to a pond or a pipe to a basin, that does not meet the requirements for national standards for SuDS in England or Wales, and I would imagine in time anywhere else. So the days of just designing a pipe system and taking it into a holding feature I wouldn't classify as SuDS approach because it doesn't meet the definition within SuDS manual or anywhere else.
Yeah. Thank you. I think we've maybe got time for a couple more questions. I'm trying to spread them out amongst attendees. Given seasonal variation, etc., any thoughts on modelling SuDS for CSO spill reduction projects where we use long-term rainfall in large network models? So I suppose during different rainfall events, you'll have different performance of your kind of SuDS features and how we kind of combat that.
Do you want one, Michael?
I don't think I can answer this one.
He's thinking on his feet. He offers you the easy one, the hard one. Sorry, Michael. Yeah.
There's a range of different things to throw into the mix there. Again, it goes back into the code of practice. There's a lot of things that have more varying reaction than what we'll get in conventional sewers. I suppose for me, if you really to simplify it down, whenever you run those long time TSRs, you will be looking at, how are the permeable spaces reacting in that catchment, and looking at antecedent wetness, and in all reality, the SuDS are no real different to dealing with the existing permeable areas within that drained catchment. You're going to be looking at it in a similar form. So yeah, I think that's a TBC longer term in terms of how we develop that. I think there's an area of research we need to look into as an industry to get standardization across industry and make sure everybody's doing it in a similar. But I think I would be averse to oversimplifying it and not giving due regard to the impact and operation of such features in terms of how they can generate loss over time.
Yeah. No, absolutely. Thanks for that. I suppose maybe just one last one. I think this is probably one that most people on the call have had. Is what's the biggest challenge in getting clients to trust modelled SuDS performance? I suppose we've probably all had that. We've all had that experience. Trying to champion these sorts of solutions, but getting pushback on how they're actually going to perform and how confident we can be in those sort of calculations, etc.
Yeah, I'm happy, Michael, if you want to give it, but we'll do a two-part answer there. You know.
Yeah. Generally I found putting the model results, putting the pre versus post, not that it's taking out the word, but if you can demonstrate and be open how the modeling's done, show the sensitivities to it, that open communication with the client should provide a bit of confidence there. Perhaps where the sometimes the industry lacks is sort of the overall visualization of features. Again, it's probably the scared of putting in like a bomb crater in the middle of a park or something like that, and dealing with perception that way. But Anthony, I don't know if you want to add in there.
Yeah, I just reiterate what Michael said. It's that communication piece, how we convey that information to the client. I think we need to become better salespeople around it in terms of making sure we are very clear around the benefits, and those benefits can be substantiated. They're evidence based. We have been very used to doing it with hard grey infrastructure, and a lot of the time it's an appreciation of the client is they've been used to those hard grey solutions over the years, that they know, well, that's the performance because we've seen it and we know it. And I think a lot of them, for me, don't appreciate that whilst the performance of grey infrastructure will generally reduce over time, that the green infrastructure can actually improve. And whenever you bring that into the conversation, you can see a complete mind shift in terms of improve. How does and then you have to go to lengths to explain, what's happening in terms of the solids and the green infrastructure, how that's improving over time. That you're maybe not necessarily going to factor in on day one, but this is how it become more resilient over time. So yeah, it's learning how to convey that and communicate that to the client.
Yeah, no, I think this, yes, I suppose, yeah, part of the challenge of all this, and trying to get it part of the kind of the day to day of these sort of I suppose placemaking, and in a lot of cases that stormwater management discussion. I think we could probably talk for another about 3 hours, even just on the questions that we've got so far. Sorry we've not been able to get to everybody, but I will just start to wrap up if I can. Just quick mention of some CIWEM events that are coming up. Another new members group event, looking at the CIWEM chartership review. That's actually that's been done. That's already gone. But we've got the new members group study weekend, which is coming up. So I think we've got a week left for people to sign up to that. Please go and have a look. We're trying to get like-minded individuals together and for some time to learn and share ideas and have an enjoyable weekend. So please look at that and consider getting involved. And we've also got, obviously, all these other events. I'm not going to go through them individually. And then we've got the UDG annual conference at the end of the year. New members group, we will be there. Hope to see people there. I think that is everything from me. So thank you very much for joining, everyone. We'll hope to see you at another event like this in the future.
Thanks, everyone.
Thank you.
Thank you.
Thank you very much for attending, and to our speakers and to the Urban Drainage Members Group for organising this webinar. It's very much appreciated.